Welcome everyone. This is our video where we're going to learn to code by making games. So episode 1, basic training. Now, chances are this is not the first video you've watched about learning how to code. So up front, my video is not like others. So instead of showing you what to code, I'm going to actually try my best to teach you how to think in code instead. Why? Because you're not going to learn by copying. You need to figure it out your way. And I am going to give you the source code, but I want you to use it for comparison and not understanding. So again, I will help you how to think, but you must do, and often. It's just like learning a sport or an instrument. So here's an example, a metaphor if you will. Athletes are trained by learning patterns and techniques, but it's up to that athlete to practice them and integrate them into their own body and mind. So a coach can show you exactly what to do to win, but it's not going to help you without you practicing and, in your own unique way. So there's a saying, the student does not become the master, he becomes a new master built upon his master's teachings. All right, so my goal is to show you how to think and code, like I said, but how we're going to do that is by breaking down an example into chewable parts and discussing those patterns involved. So what are coding patterns? Well, they're the fundamental terms or structures or recipes, if you will, that you'll find no matter which programming language you use. So I did this building a house metaphor. So if your house is like learning how to program, when you're building a house, you'll have to learn all these patterns like heating and air, or making walls or floors, electrical, plumbing, or roof. There's lots of patterns involved. But the idea is that once you understand and learn those patterns and apply them and do them many times, you're going to find this rhythm that'll allow you to do anything, from a small house to a skyscraper to a monument. The patterns are the same, it's just more, essentially. So what language will we use? You can see here there's a lot out there. Programming has been going on for a while now, and everyone wants to create their own implementation that they think is the best. For us, we're going to go with JavaScript. So since the purpose of this video is how to learn to code, not make a production grade game or application, we're going to use the most dynamic and popular language in the world, right? Again, JavaScript. JavaScript started as the language of the World Wide Web and continues to dominate the arena today. And everyone has a web browser without needing to download anything or buy anything special. So there might be some of you there that are concerned, right? Well, if JavaScript is only useful in the browser, I want to do something on the back end. Well, I'm here to tell you, don't worry. With the growing popularity of Node.js and similar technologies, if you've heard of them, JavaScript has established a foothold on the server side, right? Joining the fold of all the Javas and Cs and Golang and Fortran, etc. JavaScript is now used in the backend as well. So that means you could develop a complete end-to-end system using JavaScript alone. So learning to code with JavaScript, in my opinion, is the smartest decision you can make. So what you learn can be also reapplied if you ever need to learn additional programming languages. So what does it take to learn this whole JavaScript thing? Well, what I'm about to do may shock you. I'm going to show you some terminology representing the foundation, if you will, for successful coding of anything. You're probably thinking, how is something like that going to fit into one single view? Well, here we go. These are 12 concepts or ideas, if you will, terminology. So my thesis is if you actually spend an hour or even a day with each of these and how to apply them, you will know how to code. An hour with each of those is roughly equivalent to watching a season of television, something many of us have done. Except, when did television ever enable you to fulfill your creative dreams? Never. Okay, maybe, but who cares? Let's do a brief overview of those 12 concepts. Starting with variables. So variables hold a reference to something meaningful via a name. So here's my metaphor. If your car is the data, if you will, that you're interested in, well, your car key could be the variable that references your car, right? You would name it car key to differentiate it from other keys, such as a house key or mailbox key. You would also not use your house key to access your car, right? So variables are unique. Now moving on to functions. Functions are the lifeblood of any computer program. So they're where all the action happens. They do things and create or reassign variables. They also have a meaningful name. So imagine functions like verbs in a language. They're used to describe an action, a state, or an occurrence, right? In my picture here, this program is alive because he's doing this, checking that, going here. Those are all functions. So functions, there's two aspects in code that you'll see. There's the actual setting up at the top there of the function, and then there is calling the function, which causes it to run. So take this metaphor. Let's say you're setting up an alarm system at your house. That first piece up at the top would be you setting up and like declaring how your alarm system should trigger or behave. And then at the bottom, you would actually activate the alarm system. If you don't activate it, it's not going to be used no matter how great it is. Moving on to scope. So scope is all about isolating unrelated parts of a program to avoid chaos. Now, my metaphor for scope is imagine a bunch of homes in a neighborhood. So could you imagine living in a world where doors didn't exist? No. As a homeowner, you can access things outside of your home in public spaces, right? But things outside can't just access your home without permission. So there's a door there. Thus, your home is protected from chaos by its scope of security, if you will. Now, here's an image, and we'll break it down. So when are scopes created? So whenever generally you see those curly braces, that is forming a scope, right? There's functions have their scope, and logical blocks like if statements, they create a scope. I called logical scope there. Now look at some of those arrows. So the direction that they're going, and then the green or red. Every function establishes their own scope, like we mentioned, and they can access the outside, right? Outside of their scope, but outside cannot access things within their scope without permission. So in this example, some declaration within the bottom scope there, the logical scope, couldn't reference something in that function's scope, and the same vice versa, right? But those scopes can access the global scope outside, but again, the global scope can't reference some variable or other thing that is declared in those other scopes. So moving on to parameters. Now, remember when we talked about how scope can be imagined like a house, and the owner can access things outside, but outside things cannot access his house without permission? Well, parameters are a way to describe those permissions or agreements for what can enter your house. So in this example, you see the sad salesman walking away because the parameters to this my house scope are only friends and family. So that's a little metaphor to put that together. Now, returns. So if a function represents your house and a parameter represents what can access or be brought into your house, then returns describe what can leave or return from your house. So here's another metaphor. So think of a home business, right? The parameters of this home business would be like string and cloth, let's say. Those can be brought into your house. And what can be returned from your house home business is socks, let's say. Okay, so that function example at the bottom there would have string and cloth coming in, and then that function would return socks to whoever called it. That's returns. Moving on to data types. So most programs I've seen don't exchange string or cloth and socks, right? So what do they actually work with? Well, data types and then data structures we'll get to in a minute too. So what are data types? My metaphor for these is if you have taken chemistry, there's this thing called elements in chemistry that you learn about. So they're these foundational building blocks of all the more complex representations of matter. In coding, right, an element could be considered like a string or a number or a Boolean. Those are the foundational elements that can't be broken down any further necessarily, and they are the basis for building more complex things. So what are those more complex things? This is data structures. So ways to group data together or to scaffold more complex data representations. So following our chemistry metaphor, data structures are like compounds. So compounds are formed by multiple elements. So in my case here, like H2O, right, could be represented by an object that has like two H's and two O's. Or this lovely B28 compound could be represented by like an array full of 28 B's. There's two main types, like we said. or just covered briefly, arrays and objects. So let's dive into those a tiny bit more. So in array, I have two examples here, metaphors if you will. The first being a train. So when you imagine a train, it's pulling a bunch of cars, right? Those cars are in sequence and there's a defined number of them. So another example could be a deck of cards has 52 cards ordered, and you can access them, right? So it's just this way for you to group similar things and allow you to easily repeat logic over the things held in those array slots. Now moving on to objects. So you can represent virtually anything as an object. So here I did my car, but think of an object like grouping more than one attributes together to represent like this larger cohesive whole. So again, back to my metaphor, my car, one attribute might be that it has like 4 wheels, or that it's the color red, or it gets 20 miles per gallon. So all of these attributes combined together represent my car. Moving on to algorithms. So algorithms are a specific kind of sequence of operations, typically contained in a function that performs some useful or repeatable operation. So I find these things by searching the internet, right? I am not the super smart nerd type that maybe figured it out and provided this lovely algorithm to the world. So I search for them, I enter my problem that I'm trying to solve, and usually there's a result that is this lovely algorithm you can use. So a metaphor is if you have a deck of cards, back to that example, an algorithm would be something that could sort those cards based on its logic that it does, and then you'd have this kind of ordered set of by suit or number, value, you'd have this sorted order of cards. So that's in general what algorithms are useful for, but there's tons and tons of other things that you can do with them. Moving on to loops. So loops are used to form cycles of repeated logic, so you don't need to write the same lines of code over and over again. So I took this example. Imagine your program is representing your commute to work, right? And I have a function, let's say, that is called drive 1 mile. And then I also have a function to park. So in the top example, you wouldn't want to say in your program, drive 1 mile, and then drive another mile, and then drive another mile, and drive another mile, so on, 6 times to get to your 6-mile commute. That's plus parking at the end, that's 7 lines of code. So no, right? You can actually use a loop for this thing. Your loop would look something like 4 6 miles called drive to work, right? 1 mile. And then if you've arrived at work, you can then park. That's 2 lines of code. So this is why loops are useful. Another example here of a for loop. That's one specific type of loop. So imagine you live with 2 roommates, and you need to make food for yourself and each one of those roommates based on your requirements. So your for loop will be set up to run 3 times, right? For you, for your one roommate, and your other roommate. So the program on the left is bad because you wrote make lunch 3 times in sequence, right? You could have actually optimized that code a little bit to say for 3 individuals and then called make lunch. So it's just a tighter way. It's still, technically evaluating make lunch 3 times, but it's written in a more concise format. There's another type of loop, very common, called a while loop. So part of your program, let's say, needs to simulate watching a toddler. Your while loop would be as follows. So while toddler is awake, right, watch and care for child. That loop would run continuously, but it would stop when the condition of child is awake changes to false, so i.e. they're asleep. So that program on the left is bad because you're calling watch kid, check awake, watch kid, check awake over and over and over again, right? That could actually look like a while loop where you check while kid is awake, it calls watch kid until kid awake is not true anymore. All right, moving on to iterations. So unlike loops, iterations require a data structure such as an array or object to exist first, and then much like a loop, the idea is to examine each member of that data structure in sequence. So here's a metaphor, examining a train car in sequence, right? I have this train array, it's full of 3 cars, and I want to iterate over each one of those. So there's a lovely function built into most languages called for each, and it pivots off of a array or even an object. It looks a little different, but the idea is that it will give you a reference to each car in that array in sequence, and then you could do something with that. All right, moving on to math, logic, and operations. So many of us learn these things in early schooling, but I have an example. Say you're invited out with your friends and you say yes, and then your girlfriend or boyfriend invite you out after that, right? What do? You immediately go to evaluate all these scenarios. So there are two conditions that'll be represented as the top level if or else at the top here, right? So if my girlfriend is happy with me, else, that means she's not happy with me. And then there's certain subconditions within those conditions, right? So let's just go through this. If my girlfriend is happy with me, and then inside of that, let's say that's true, if I chose my friend still, maybe things are fine, right? She's happy with me, it's okay. Now, if I don't choose my friends and I switch it up on them and say, hey, I'm gonna actually hang out with my girlfriend instead, my friends will shame me. That's that inside else statement there, right? But going back, if it was false initially, that my girlfriend is actually not happy with me, and then I choose my friend still, right, things are bad. But if my girlfriend is not happy with me, and then I choose to go with her, right, things are fine with the girlfriend. So it's just this way of like evaluating conditions, and then there's subconditions, and this thing can go on and nest for a while depending on what it is. But this is, basic logic. Check condition and then check other conditions inside of those, and it's nice and organized. Let's touch on user interface. So with JavaScript, right, you're going to want to learn HTML and CSS in order to most effectively render some functionality of your application or game to someone who's going to use it. Now, touching on libraries and packages. So libraries and packages are typically used via functions, and those functions perform some sort of logic that another programmer created and published for use by others. So that saves time and energy, right? You are, as an individual programmer, not having to solve the same problems over and over again because someone published a library or a package that does some useful thing. You can just download it and use it. So take this metaphor for a package. Let's say you want to eat beef Wellington for dinner. Two options are to make your beef Wellington from scratch, and right there you're thinking it's probably not going to be that good, and think of the dishes, right? Or you could go to a restaurant and aka library and order a beef Wellington off the menu, and then the thought there is delicious, right? So using these libraries is kind of like using a restaurant. You're going to get a predefined experience by a great chef rather than doing it yourself. So moving on to the topic of JSON. So JSON stands for JavaScript Object Notation. It's a human readable kind of object representation that can easily be transmitted between separate programs or even stored in a file or database. So my metaphor for JSON is if you yourself are represented by a driver's license, let's say. That driver's license is a human readable, transferable representation of your identity. Many things know how to use it. So the same thing could be said for JSON. Your attributes and properties, if you will, could be represented in a JSON object, right? In that example there, you could put your age, your height, your hair color, your weight. Anything you can imagine could be represented in JSON. And the last topic of debugging. So debugging is the heart and soul of coding. When you run a program, things are bound to fail initially. So debugging is finding out what went wrong and fixing it. So something for JavaScript and web development in general is developer tools, right? They are your friend. So in a browser, there's if you right click, or there's other ways to get to it, but there's developer tools menus that have all sorts of useful features for what went wrong and exactly what line and character it found it at, so you can kind of figure out what's going on there. All right, that completed our basic training. So 12 topics. Let's wrap up, I guess, by seeing all of these topics together to create our first game. So our first field exercise, if you will, is going to be talking through how we're going to make this game called the guessing train. Now, like I mentioned, I'm not going to show you what to code. That's not going to help you. Instead, I'll guide you through how to think in code, and you must figure out the details on your own. And ultimately, you can view my source code. So the idea is you'll have a train that is pulling 7 cars, and each of those cars is holding a number 1 through 7 in some random order. Your job is to find which car contains the number 7 in as few guesses as possible. And then game over is shown when the 7 is found. So let's talk through these 12 concepts with the example of this game. starting with variables and data types and structures. So I'm going to represent my train as a variable that equals an array of 7 with 7 slots containing numbers, right? And those numbers are going to be 1 through 7 in some random order. So we're also going to create another variable that's the same size array, but the contents are going to be booleans, true or false, and that way I can keep track of which slot I've checked, right, at a given time. I might check the first one, then the second one, then the third one. That boolean array is going to be true or false depending on if I've checked it or not. So then 2 more variables I'm thinking through that I might use to track maybe when the game over condition is found, and then which car position the 7 was found at. So adding on functions and scope algorithms. So I need to find an algorithm and create a function to use it that will randomize the number placement in my train array, so no cheating is allowed. If you know the order, you're going to know where the 7 is. This thing's going to randomize that order. So, and then I also need another function to check the train car at a given time. And it's going to we're going to evaluate scope in that instance as well, just to clarify some of that stuff. Adding parameters returns basic math and operations. So my check train car function will take a parameter of which position is desired to be checked, and then it will return true if 7 was found, or false if anything else was found. So right, that's logic and operations there. Adding in loops, user interface, and libraries packages. So we will need to add a user interface to display which cars have been checked, and that's going to be by iterating over my checking array. As well as, input controls allowing me to make those guesses and then display the score and game over. That's all user interface. So we're going to leverage built-in libraries for accessing HTML elements in JavaScript and then setting up user input events as well that will progress our game. So finally, adding JSON and debugging. There's going to be debugging along the way, inevitably. That's always a part of programming. And then when the game is over, we're going to create an object actually out of all the main variables and print that object to the screen in JSON format for your reading pleasure. So, summary, thinking in code. 4 variables. 1 is an array of numbers, 1 is an array of booleans, 1 is a boolean itself, and then 1 is a number, right? And then 4 functions. One of them being an algorithm function that I found on the internet. That's going to randomize the positions of that array. And then the other one's for setting up events for player input, 1 to check train cars, and then 1 to update my HTML after each guess. So my solution had 4 variables, 4 functions, 1 found from the internet, 3 lines of HTML if you exclude the standard boilerplate tags, 56 total lines of JavaScript. So what is the difference between our game here and a program used to, let's say, launch rockets into space? It's actually almost nothing except more time involved. So every single program is comprised of these fundamental concepts we just covered. Now, breaking down ideas with these concepts is how you will be thinking in code. So thank you guys. I gotta show you the game. So we're gonna enter a guess. I'm gonna start with position 1, and that looks like number 1. I can check number 2, that was 3. I can use this arrow, check position 3, check position 4, 5, 6. It looks like it's all the way at the end here. Boom. So 7 was hiding in position 7. So you can see all the output here, and that's the game.